Alright, this is our second video on benzene substituents. It's mostly going to look at phenols and ipso substitution. Last reaction that we'll talk about with benzylic carbon. So you actually can have a benzylic ether using our hydrogenation. Again, remember that CO bond is going to be a little bit weaker, so you can hydrogenate that into a toluene example here. Not a very important reaction mechanistically, but another feature of that benzylic position. We're going to focus mostly on phenols here. So phenols are going to be a hydroxyarine. That's going to be a OH group on a benzene ring. You'll notice the equilibrium of this. While it looks like a ketone would be favored, the ability to have an aromatic system with the alcohol, it's one of the only systems we see where the enol form would be preferred because of the aromaticity of the ring. Nomenclature with phenols, very similar to what we've seen with carboxylic acid derivatives. And you should have seen some of this with your benzene nomenclature from chapter 15 and 16. So you would have a 4-methylphenol, 4-chloro-3-nitrophenol. So here, make sure your numbering goes okay. In the case, if there's a carboxylic acid, remember your nomenclature priorities. The carboxylic acid takes precedence, so this would be a 3-hydroxybenzoic acid. Make note that your hydroxy group is the name for a OH group as a substituent. Phenols are actually pretty acidic given the circumstances, right? So we know that carboxylic acids are very acidic. These are going to be right in the middle between carboxylic acids and traditional alkanols, so very familiar alcohols. So if we end up giving off that proton, we can then stabilize that negative charge, something we talked about in the last chapter about how that's going to be stabilized throughout the ring through resonance. So not at much of a disadvantage. So let's talk a little bit about phenol synthesis. The way we're going to do that is nucleophilic aromatic substitution. Notice the difference here. We've only talked about electrophilic aromatic substitution. This mechanism is going to be another additional elimination pathway, so we have talked about those in the recent chapters. And this specific type of reaction is going to be known as ipso substitution, where we're displacing a non-hydrogen group off a ring. So we have not seen ipso substitution. All your reactions before, we're always looking at removing a group or adding a group, replacing it with hydrogen. So these are our first reactions we're talking about that can do this. So we would have a nucleophile looking at a halogen. Our rules still apply from all our basic chemistry where we need a good leaving group. Most of the time for this is going to be a halogen. So we can have a nucleophile add at that position. Let's take a look at some examples. Here we have water with a strong base, so we're going to end up adding our phenol. You can also do this with a stronger base such as ammonia, where you would add an amine. In order for ipso substitution to work, you need to have a strong electron withdrawing group located ortho M-pair to the leaving group in order to stable out the negative charge. So we will look at this mechanism in a second. So in order to do this, our addition is going to be very similar to what we saw with our benzene substitution reactions. Our nucleophile will add to position with the chlorine. Electrons will be pushed out onto the ring, and I don't have all the resonance structures included here, but you can move the resonance around completely to the other nitro group, and it's advantageous. Why we need those nitro groups is because we can include the resonance out through them. So it adds to the stability of this anion we've created. Once it moves around to the other side, or you can do this as your second step after you add your nucleophile, you can drop that negative charge down, kicking out your chlorine, and we have ipso substitution with our nucleophile being replaced at the position of the chlorine. So if your electron withdrawing groups are meta, your ipso substitution will not occur. Let's take a look at really quick why. If we add our nucleophile here, notice my two nitro groups are meta now. Our negative charges are not able to extend out into the nitro groups, sort of limiting the stability of this structure. So there's not enough energy to allow this to happen, so you need to have those electron withdrawing groups, ortho and para. Another way benzene can react with it, if it has halogens, is through another mechanism called the benzyne intermediate. We have ipso substitution occurring. Notice we don't need any electron withdrawing groups here, but we can have our groups that are in pink replace our chlorine. So we can create a phenol this way. We can also create a amine this way as well. Notice here that our conditions are much more strenuous than what we saw in the previous reactions, and it's because we don't have that electron withdrawing group there to help stabilize that intermediate. So when we actually add our new nucleophile, we see that it adds to 2 different carbons. So if we, this is actually done using radioactive labeling, making that a C14 atom. And so we can see that certain times the NH2 will be on the carbon that the chlorine was attached to, other times it will be next door. Now we know that without any other substituents, these 2 products are the same. But there has to be a reason why sometimes it would stay on that carbon and sometimes it wouldn't. And we'll look at why with a new mechanism. So our first step, it's actually going to be the reverse from our last step. We're going to have an elimination and an addition. So our base is going to pull off one of those hydrogens, giving us an anion that's going to drop, kicking out our halogen, and giving us our benzyne triple bond in the ring. This mechanism, first step, should look worrisome to you. There's a lot of red flags here, but it does end up happening because we can track the production of benzyne in situ, and while we won't isolate it, we can verify that it exists. This is problematic for a few reasons. One, we know benzenes are not very acidic, so taking that hydrogen is going to be very difficult. In addition, that negative charge is not resonance stabilized, so it's very reactive. It's not going to want to be even generated. And then their last reason is that that angle strain on a ring is going to be very difficult for having that triple bond inside. Our second step is going to be addition, so we can have our amine be generated at the carbon that originally had our halogen on it, or we could have it at the other position. And so this should remind you of addition to a double bond where we'd see about 50% of the product if we didn't have a more substituted side. So in this case, since it's the same, it's not going to matter. So another thing we can do with phenols is if we add base and a haloalkane, we can pull off that hydrogen on the phenol, have that oxygen act as a nucleophile, and we can generate an ether. This is also known as the Williamson ether synthesis. You may have talked about this earlier in 118A or B. Extending to that, we can also use a halide or an anhydride with a strong base, again pulling off the proton from our phenol and having that act as a nucleophile. So this is an additional way for us to make an ester off the ring. We also have some review. The reactions we talked about in chapter 15 and 16 still apply. So we would have an OH acting as an ortho-para director, so we can still add a nitro group or para. And one thing we didn't necessarily discuss, but you can actually halogenate a phenol. You do not need a catalyst. It will add multiple times with lower conditions. You will have a monobrominated product, especially if you can block the para position. That's it for benzene substituents 2.